Well, hello and welcome to our 46th and final session in our course in Introduction to the Theory of Semiconductor Devices. So, in today's session, we're going to have a quick review of the HEMT design and design considerations, and then we're going to move over to the IV characteristics of MESFETs, and we're going to compare that to the MOSFET. We've done a lot of work on the MOSFET, and now we're going to go back and very briefly do the same thing with the MESFET, and we'll see some rather interesting similarities as well as differences between the characteristics of these two really important devices. And then we'll end with another novel device called the Static Induction Transistor, or SIT. It's a device that I have a personal affection for because I worked on it for quite a number of years. And then we'll wrap things up. And let's get started with the 1989 production of Showboat, Why Do I Love You? And we'll see you in about a little less than 4 minutes.
Oh, I'd love to see you act. I know I'll never make it to New York.
Why don't you give an impersonation of your ma singing, Why Do I Love You? Now, just a sample.
All right.
Why do I love you? Why do you love me? Why should there be two happy as we? Can you see the why or wherefore? I should be the one you care for.
That's how my mother, Magnolia Ravenel, sings it. But here's how we sing it today. You're a lucky boy. I am lucky too. All our dreams of joy seem to come true. Maybe that's because you love me. Maybe that's why I love you. Woo!
Welcome back, and here are some of the topics we'll be covering in today's session, our last session in our journey we're going to have a quick review. I didn't realize it doesn't seem like a lot of topics, but there's a lot to cover. So we'll quickly review the hemp design, and then we'll go on to the current voltage characteristics of the MESFET, and we'll be comparing those, specifically the current, between the MESFET and the MOSFET. They're very different structural devices. They look certainly a lot different, and yet they have quite a bit of similarities between them. And then finally, we'll be looking at a novel device called the static induction transistor from the fabrication perspective only, and then we'll wrap things up with our, well, you'll see, it'll be fun, and the final video clip, which is a nice way to end our journey, finale to Showboat, You Are Love. Love's a nice way to end things up. Okay, so let's get started on the review of hemp design. This is a cross-section of the high electron mobility transistor. We have a metal gate, generally gold, deposited on top of a deposited laver, which is heavily doped aluminum gallium arsenide. It is a very wide band gap and low affinity, and that is deposited onto something which we haven't shown here, which is a spacer level. The purpose of the spacer level is to ameliorate or to reduce a little bit of all these positive ions, fixed ions, in the depletion region. The depletion region in the AlGas is complete. The AlGas layer, we like to think of being as completely depleted, so that all of the conduction from the source to the drain occurs in the essentially intrinsic gallium arsenide. Where does the channel come from? It comes from electrons which are dumped from the heavily doped N-type AlGas layer. They're dumped into the gallium arsenide layer. And just like in the MOSFET, we had the very wide band gap SiO2, and then we had a notch forming at the surface of silicon. So the same thing happens in the hemp. So here we just have a little bit bigger region here, which is blown up, and we want that T1, which is the distance from here to here, and T2 plus T1 equal to T. So this requires that this total thickness here is somewhere on the order of 200 or 300 angstroms, not microns, but angstroms. Okay, and that's, we showed this the last time. We got an order of magnitude for the width, the depletion width, which was about 100 angstroms or so, or T1, and that's also would be about the same for T2. So that's what we have there. And let's see. Oh, that's about it. Anyway, just the summary of the MOSFET compared to the hemp, which was mentioned before. We have a notch formed in the MOSFET and electrons in this quantum well, and we have exactly the same thing happened in the hemp. The thing that characterizes both of these notches here for the MOSFET, here for the hemp, is they are extremely thin. I think 50 angstroms is probably a little bit on the high side. Anywhere from 20 to 30 angstroms in both cases. Unlike the gallium arsenide MESFET, where the deposited channel can be thousands of angstroms thick. So that's a similarity between the MOSFET and the hemp, and different from the MESFET. Okay, so let's go back to the MESFET, revisit. And here we have a cutaway drawing. The yellow is the deposited channel, definitely not to scale. This is maybe 2,000 angstroms or so. And here we have the metal gate, which would be probably gold if it's gallium arsenide, perhaps 1,000 angstroms in that range. And here we have a positive VDS. How do I know it's a, we do have a VDS because the depletion region is not horizontal. If we had VDS equals 0, this dotted line here would be horizontal and would only be a function of the gate voltage. So with a positive VDS, we are more narrowed, I was going to say pinched off. If this guy right here would go down and completely close off the channel, then we would be pinched off at the gate. The channel width, the width that current exists, that charge can flow, is called T, and that's a function of Y. It is maximum over here. This actually should really be right up here. Perhaps if I wanted to make it a little bit more clear, I should probably have put this line up here because the channel voltage is actually 0 here. But the point is that the channel is wider at the source and narrows at the drain. So we'd like to know what the voltage variation is, specifically the channel voltage variation, as we go from the source to the drain. A is the complete deposited channel, and of course A is then equal to H, which is the depletion region width plus the channel width. So equation 24.2 just states the fact that the current is constant. The current is not a function of Y. However, the resistance is a function of Y. Higher here, lower here. So I can then put this equation basically substituting for resistance is equal to the resistivity, which we're going to look at in just a second, multiplied by the ratio of dy, this distance right here. I should have put the other end of the arrow here, but in fact, let me do that now. It's dy divided by the cross-sectional area. So the units here are units of inverse centimeter. The cross-sectional area is the width into the paper, into the board, multiplied by this thickness, ty. So it's just A minus hy. We're going to be using the depletion width as a variable. So this, in the parentheses here, would be ty, and then the resistivity is the electronic charge, 1.6 × 10⁻⁹. Sometimes you write this as E, sometimes you write it as Q, doesn't matter, mobility, and then the charge density. So this is MeV, where we've basically gone further and separated out the materials parameter. So these are all materials parameter. These are not variables. And W, again, is this width into the paper. Okay, so that's basically what we're saying here. Definition of the resistivity and the relationship between the resistivity and the resistance is just resistivity multiplied by L divided by A, where L is any distance along the channel. In this case, this would be dr, and then L would be dl. Okay, so we put all that stuff into our integral. We're integrating along the channel. I probably should have put a dV channel here rather than just dV, because this is integrating along the channel. And of course, the right side is pretty straightforward. The right side is just dy times id. So that is just id times L. Now the left integral is a little bit tricky. We're going to see how that plays out. I basically just extracted an A from here. That's why this looks a little bit different. So in order to evaluate this integral, this again should be dB channel. Here, I need a relationship between H and dB channel, or H and B channel, and that is provided by 24.4. This goes back to equation, or chapter 20. Let's just do a real quick units evaluation to convince ourselves that this indeed is the case. Of course, H is units of centimeters. Units of permittivity are coulombs, joule, centimeter. This is permittivity for a aerial capacitance, and VB, and all of this stuff. Every one of these, there's only 3 terms. All the 3 terms have units of joules. That's what we have here. And then 1 over QND. The units of ND are numbers per cubic centimeter. That's why we have cubic centimeters on top. And then we have coulombs on the bottom. And the coulombs cancel out. Joules cancel out. Centimeter cubed divided by centimeter squared. And voila, we're okay. So this equation is not only reasonable, it's correct, and you can check it from chapter 20. Okay. Also from chapter 20, we have this thing called pinch-off voltage, and that's defined when the entire channel is pinched off independent of VDS. The voltage VG is such that this line here becomes a horizontal line right at the positive channel edge, so no current can flow. And that is what we call pinch-off voltage. Okay, with all that good stuff, we can substitute in for H here, and we can integrate. And again, we're integrating along the channel. So we have a 1/2, so we're going to get a 3/2. That reminds us, or certainly reminiscent of the MOSFET. We take out some of this gooky stuff over here, and we call it G0, which is the conductance, and it is as units of inverse of resistivity. Okay, so that is now the expression, or at least proportional, the current in the MESFET, and it has the 3/2 power. We can put in the limits, and we find equation 24.8 gives us an expression for the current in a MESFET as a function of material parameters, and this thing called the conductance multiplied by a number of terms which have the drain to source voltage, which obviously we need to get a drain to source current, and a gate voltage, and and this thing called VP0. And again, this 3/2 power is reminiscent of the bulk charge theory in the MOSFET. So we really see some very nice similarities here. VBI is, because this is a Shockley, VBI is the inherent barrier in the metal semiconductor Shockley barrier. Okay, so that's pretty cool. And of course, if we put in VDS equals 0, this term goes out, and then this term goes out, and then of course we have just VBI minus VG, 3/2, VGI minus 3/2. So these two terms go out, and we get as exactly as we would have hoped for, if not expected, or prayed for, as the case may be, that the current would be 0 if the source to drain voltage is 0. So let's take a look at 2 limiting cases, very small VDS. VDS much less than VBI minus VG. And in that case, we would expect, well, if we go back to the MOSFET, we would expect something that would be in the linear region, not where we want to operate at all. So these lines here would be, well, I would say quasi-horizontal. They have a little bit of a downward slope, but not too much because they have a very low drain voltage. So let's see if we can put that in. And if we put in that condition into here, we can do a first order expansion. 1 plus x to 3 halves is approximately 1 plus 3 halves x. Okay, so 24.9 is basically 24.8, where we just pulled out this term here. So we just pull that thing under the parentheses, and so this is just high school algebra to get from 24.8 to 24.9, and now we can use this first order expansion. And when we do that, let's see how that works. So we take this term right here, and we use use this first order expansion to get 24.10. Do some of the little bit of the algebra here, and now we get a square root term as far as in front of VDS. And again, this is the linear region. It has a material coefficient, well, not quite material because we do have VGI in there, but for a given VGI, all of these are constants, and the IDS as a function of VDS would be linear. So just two limiting cases within this limiting case, when we have VBI minus VG equal to the pinch-off voltage, we would expect everything to be closed off, and indeed this term becomes 1, so we have IDS equal to 0. If the entire channel is pinched off, that would be right down here when VG, the gate voltage, is equal to the pinch-off voltage. That's the definition of the pinch-off voltage. It's that gate voltage which pinches off or closes off the entire channel. So that's exactly what we have here. And let's see, the other thing is when VG is equal to VBI. VBI is this inherent barrier in the metal semiconductor channel, so that's when we're fully opened, at least at the source end. And in that case, then IDS, this term will go to 0, and IDS is equal to G0 times VDS, because at the source, at least, we are full open, and at the drain, we have just a little bit of voltage, and so we have a thing acts like a variable resistor, whose resistivity or resistance is 1 over G0, and we're in the linear region. Not a good place to operate. Okay, so now let us continue. And these results are summarized in figure 2421. And what we have here is for a very small VDS. This top line here may have just a tiny, tiny bit of a downward slope. This part at the drain will be somewhat lower than at the source, but if the VDS is small, the difference will be very small, and the slope will be small. But increasing VDS, the slope gets bigger and bigger until finally we reach VD sat at the pinch-off at the drain edge. This is exactly what we have in MOSFET. The only difference being that in a MESFET we have a deposited channel here, which may be, oh gosh, I'm kind of off the top of my head, anywhere from 1,000 to 3,000 angstroms, whereas the inversion region or version width we don't even talk about it. This thing called T inversion or a MESFET is it's a quantum well, and it's just at most a few tens of angstroms. So that's really the only difference here. So this point right here will be pinch off. We say, let's close. Well, it's not completely closed. There's a tiny, tiny little bit of opening, so the charge can just kind of squeeze in, and then this line will continue to move to the left as VDS increases above VDSAT, and we have a very large electric field which sucks up the electrons when they get to the end of the channel, and we divide the channel into two parts, just like we did in a MOSFET. Okay, so now we want to define what this thing VDSAT is. So because the channel is pinched off, we define VDSAT by equation 2413. And 2413 certainly doesn't look like the way we define VDSAT or a MOSFET, but we'll see that if we massage things a little bit, we can get this guy, or the definition of VDSAT, to be pretty much what it was for the MOSFET. Now, as the gate voltage becomes more positive, this guy goes down, is minus the gate voltage, and in order for this equation to hold, VDSAT must compensate by going up, and that's exactly the kind of behavior that we saw for a MOSFET. The VPO, the pinch-off voltage, depends only on the material parameters, namely the thickness A and the doping of the deposited channel. Generally, deposited channel has doping a little bit less than, actually about an order of magnitude less than for a MOSFET substrate. So MOSFET substrates will have substrate doping above 10 to the 17th. I think they're getting into the range of 5 times 10 to the 17th, whereas the channel, deposit channel, will be on the order of 10 to the 16th, maybe a little bit above that, but probably less than 10 to the 17th. And of course, one of the reasons we can get away with that is because the A is so big here. The A is huge compared to the T inversion. Okay, so now let's rearrange this. We're going to work on this crazy thing called VDSAT, and we put VDSAT on the left, put all the other gunk on the right, and we see that the VDSAT depends on VG. Makes sense. VG goes up, and VDSAT goes up. Plus, we have some material parameters. So all of this, these material terms, these are going to turn into magically the threshold voltage. So we'll see that in just a little bit. So at least so far, we have similar kinds of behavior. VG goes up, VDSAT goes up, and this kind of looks like it's, at least has some potential. And that's what we're going to show right now. So we go back to 24.9, somewhere's here, and we rewrite this thing, and we're going to see what we can pull out. So, where is that? Okay, that's right here. So whenever we have VDS, we're going to substitute VDSAT. So this is the equation for the saturation current as a function of the saturation voltage, including the gate voltage, the pinch-off voltage, and this variable barrier VBI. So this is equation 2409, and now we're going to massage this a little bit. And the first thing we do is we take a look at this guy right here, and we substitute. So VBI minus VG minus VDSAT, that is just VPO. So all this works out to be VPO to the 3/2. This term we keep, So that looks promising. Okay. And now we continue. Okay, so now we substitute for VD-SAT. Back here or here, doesn't matter. This guy, so we substitute the three terms for VD-SAT. Now this guy turns into all this, and here this remains the same. And finally, we pull out a VP0 out of this whole mess, and lo and behold, we can define something now called the threshold. And so we didn't do anything here, but in going from this line to this line, we just defined VB threshold as VBI minus VG. So this thing becomes minus V threshold, and here we have, where we see the VPO, we just, well, actually, it's this guy right here. VBI minus VG would be the threshold. So we're pulling out a VPO. That's why the 1 comes in here, and that's pretty much it. So now, let's see. Yeah, we also expanded this parentheses here to bring the VPO in square root. So this guy comes under this 3 halves here. It was 1 half, and we have 3 halves on the bottom, which is a minus 1 half, or 1 half on the bottom. Okay, so that defines the threshold. So now we can rewrite this term right here, and look at that. Isn't that cool? If we define V threshold as VBI minus VPO, we have VD-SAT here equals VG minus V threshold, because V threshold is VBI minus VPO. So how cool was that? So that is exactly the same thing that we had in the MOSFET. This is precisely the same equation, or definition, I should say, for VD-SAT. We just had to define our threshold a little bit different, but everything else is exactly the same. And almost everything that we said for the MOSFET carries over to the MESFET. Well, not everything. If VG is equal to V threshold in the MESFET, then VD-SAT is 0, and I get no current whatsoever. Or maybe a little bit of current, but not too much. This is not, I should have made this in capital letters, this is not the case in the MOSFET. Even at threshold, we can have significant current. We may not want it, but it is certainly there. So, what's the conclusion? If we made laptops out of MESFETs instead of MOSFETs, at least in theory, they wouldn't overheat. They could stay on our laps, and our laps would be cold or cool at room temperature. And the batteries would, they might last a lot longer because there's very little, if any, leakage current. But at least above V threshold, if VG is above V threshold, then the performance or the equations are reasonably similar. For gate voltage above threshold, we have a channel voltage, we have a finite positive VD-SAT, and we have an IDS, certainly, and if we get to a gate voltage of VD-SAT, then we have ID-SAT. So as VG becomes even more positive, the output current increases further until it gets to VD-SAT, like I just said, and then we have ID-SAT, and then at above VD-SAT, the IDSAT, the current, does not depend on VDS. We have saturation, and we have a preferable or desirable area of performance, the saturation region, in which the current only depends on the gate voltage, and that is a really, really good thing. Okay, so let's trudge on again. We take a look at the last line of equation 2415 right here, and we rewrite that. It's 2417, and now we're saying if the difference between the gate voltage and threshold voltage, this difference right here, is close to VP0, then we're going to use a binomial expansion to see what that takes us. So this term is going to be very small. So this is the term we're going to expand. And let's do that. And we have rewriting the equation 2417. And what do we do here? We must, here we just expand break apart the parentheses here. So it's 2 VPO divided by 3. That's this guy right here. And then we multiply this guy by, put it right here. And we just bring this down. And now we're going to expand, use a binomial expansion right here. Let's see what happens when we do that. We bring down the 3 halves, 1 minus all of this gunk multiplied by 3 halves. So that's what we have here. This is the binomial expansion right here. So we use that here to replace all of this with this, just using this approximation. And what do we get? Yikes! We get no current. That is obviously not good. So what is the solution to this conundrum? Well, we didn't use enough terms. Whenever we take a binomial expansion, good idea to just use the first two. You can't use the first term, it's just one. Now, that's pretty straightforward. We have to have at least 2 terms. And we saw this. There was one case where we saw this before. I think we were doing sub-threshold region in a MOSFET. So what we need is another term. So we need this guy here with a square term. So this is first term, second term, and the third term. Now the good thing is we know these first 2 terms give us 0. So we don't have to worry about that. We don't have to put in this whole expansion, which would be a nightmare. All we have to worry about is the last term. So we basically replace this thing with just that one term, and we get immediately, actually, a final expression for the drain current, saturation drain current, and there it is, right there. It is 3/8, which is 3 divided by 2 times 2 times 2. That's where we get the 3/8, and we get a square term. And now we also substitute for the second G0, and here we get equation 2422, and that is exactly what we expect in the saturation region. IDSAT is equal to a square law VG minus the threshold with some coefficient, and that is exactly what we had in the MOSFET. IDSAT for the MOSFET, coefficient multiplied by VDSAT squared. The thing in the parentheses, of course, is just VDSAT. So these are really almost precisely the same. They're just little definitions, little differences in the coefficients. So this is a big deal. Equation 2422 is very, very good. And there's 2 factors or 2 little statements we can make or equation 2422. The drain current, IDSAT, depends only on the gate voltage and not on VDS. If it depended on VDS, we would have a voltage controlled resistor, which is not good at all. But that's exactly the kind of behavior we had in for the saturation current in a MOSFET, and that is, well, I said, of course desirable. It is, I should have put in a very desirable. That is where we want to be. And there also is a square law dependence. Just like we had for the MOSFET, we have square law dependence for the MESFET. Where you say, well, what happens to velocity saturation? We know that this really is not a square law. This too is something like 1.3, 1.4. How about here? Do we have velocity saturation in MESFETs? And the answer is yes, but I hope you are at least tempted enough to want to find out what the issues are with velocity saturations in MESFETs, and that requires a whole course on wideband semiconductors. So we're not going to be able to go into that here, but that is a fascinating issue. Velocity saturation, you bet it occurs in MESFETs. It's just so you have to look at it a little bit differently. Well, we can even go further. This thing about here is you say, oh gosh, these coefficients look so different. Is there any way we can get this thing to at least resemble this? And the answer is yes, or I wouldn't have asked the question. Okay, so we substitute for G0, and let's see, here sits G0, and we substitute for VPO. Here sits VPO in terms of A squared. We have an A on the top, A squared on the bottom. You get an A here. Now it's beginning to look a lot like the coefficient here. W over L with a mu, W over L. Wow, that's great. And the only thing we're missing now, what is this epsilon over A? Well, permittivity divided by distance is a capacitance. So we're going to it's actually an areal capacitance. So we define permittivity divided by A as C. So C is the areal capacitance of the channel layer. And now we get something which is almost precisely, actually it is precisely, like the MOSFET. It is mu W over L, some capacitance divided by 2, and the only difference is the capacitance. The capacitance of the depletion region of the MOSFET is extremely. No, I'm sorry. This is not the depletion region. Sorry, this is C-ox. Yikes, stupid me. So this is the capacitance of the oxide layer. Sorry about that. It's a little brain stupidity. So when the MOSFET, this would be epsilon divided by T-ox, not T inversion, T-ox. Well, T-ox is what, 20 angstroms? Whereas A is on the order of 1,000 angstroms. So the C here is much, much lower, and that is not good. What is much, much higher, and I'll say much, much because it's really much, much, whereas the C might be in order, a couple of orders magnitude lower, the mu is 3, 4, 5 orders of magnitude higher. So we get exactly the same coefficient. We just have to interpret the C and a little bit differently. C is not so good. Mu is really, really good. Okay, so now we have the summary of the comparison of the MOSFET and the. Okay, so the first paragraph basically says tells the similarities, not completely. Of course, on the MESFET, we have a metal, generally gold, and the MOSFET is generally doped N+. Okay, so, but everything else is pretty much the same. Very significant and glaring similarities between the MOSFET and the MESFET. And I would suggest that fact that they are so similar is really quite amazing because they're formed so differently. I mean, in the MOSFET, we form a channel by inverting the surface of the substrate, whereas in the MESFET, we have a channel which we deposit. So those are such different formations. The fact that they behave so similarly, I think, is really quite remarkable. In strong inversion, any increase, and this is for the MOSFET, an increase in the gate voltage appears solely across the oxide. That is very similar to what we have for a MESFET. The gate voltage, again, this is for the MOSFET, controls the magnitude of the inversion layer and, of course, the channel resistivity. Unlike the MESFET, in which a channel, and this is a big one, unlike the MESFET, in which a channel is buried under the depletion region. Remember, the MESFET, the depletion region, is above the channel. It is right below the gate because we have a Shockley barrier. A Shockley barrier always has a depletion region right below the metal. In the MOSFET, the inversion layer is below the channel. So those are very, very different. And that is chalk one up to the MESFET because we have on the MOSFET lots of surface scattering off of that depletion region. So the MESFET has some advantages there, but a lot of similarities and a few dissimilarities. So let's put that in the table form. In the MESFET, of course, we have a deposited channel, deposited epitaxially, same taxi layer. MOSFET, the channel is created from minority charge in the substrate, or in the case of a MOSFET, actually, much of the charge comes from the source and the drain because they're both heavily N-doped. Channel type in the MESFET is a Shockley barrier. Channel type is field across the gate oxide into the inversion layer. This is the big one. The channel position is buried under, I should have made this capital, there's capital letters, it's buried under the depletion region. Here the channel is at the oxide silicon interface, and it is above the silicon substrate. So that's an advantage of the MESFET. Here's another very interesting dissimilarity. The depletion region for the MESFET is opposite in sign to the channel. For example, the depletion region in the gallium arsenide N channel MESFET, the depletion region is positive fixed ions, where of course the channel is negative. Whereas here in the MOSFET, the depletion region is the same sign and always the same sign as the channel. If it's NMOS, the depletion region is negative, and of course the channel is negative. And the depletion region is continuous with the gate metal, which is basically just another way of saying that it is above the channel. It is contiguous with the gate, so its channel is buried underneath of that, whereas in the MOSFET, the depletion region is buried under the inversion layer. So that is that's another dissimilarity. And the drain voltage comes from above in a MESFET, and it comes from below in a MOSFET. That's why we can deposit the source and the drain in a MESFET, whereas we have to implant the source and the drain in a MOSFET. The last device that we will be studying is the static induction transistor, or SIT. And this is certainly a novel device. It has a long history. I believe it was first invented back in the 1950s, but it did not find even limited utilization until, well, I think that's a little bit generous, probably 1990s more likely. And one reason that it is limited even today is because the difficulty in fabricating the device. But it is kind of a modified MESFET, which means it has a Shockley barrier for the gate, and because it has a Shockley barrier, there is a depletion region adjacent to the gate, but that depletion region is generally not sufficient to pinch off the gate with no applied bias. So we're going to have a channel which is there, and we're going to have to pinch it off by, or control the channel by the gate voltage. Okay. Unlike the gallium arsenide MESFET, which is a horizontal device, the charge flow is from source to drain in the horizontal direction. In the SIT, the channel, everything, I should say, the whole device is vertical. So here is a schematic diagram. The charge flow is from source to drain, and it's up to down. So it's a vertical device rather than a horizontal device. The whole thing is made on silicon carbide. Silicon carbide is a very nice material. It has some advantages. It also has some disadvantages. First, the bad news, it cannot be grown in 15-inch boules like silicon. I believe the highest even today is 4 inches. So the number of devices that we can pack onto a wafer is severely limited. Now, for the good news is that it is hard. It's hard to break, so it's great for fabrication, unlike gallium arsenide, which is very fragile, and it is impervious to high temperatures. It has a wide band gap, so even at 500 degrees C, we're essentially intrinsic, whereas at 500 or 600 degrees C, silicon starts to have a very high intrinsic concentration, and gallium arsenide can't even stand up to those kind of temperatures. So it's very good for high temperature environments, and it's very good for high power applications. So here in figure 2422, we show in color code, we show metal, which is in green, the source contact, which is deposited as an not as an afterthought, but in the back end process of a gallium arsenide MESFET. This the source in a SIT is actually part of the structure. So we'll see that in just a minute, and that is in turquoise, and the channel is in yellow. So we have three different colors, and here we show the charge flow. The gate controls the depletion region, and the channel is now depleted, or partially depleted, and the dotted arrow shows the charge going from the source into the drain. Now, one of the also differences between a SIT and a gallium arsenide MESFET is when we buy a gallium arsenide wafer for processing, we buy it with the channel already deposited. When we purchase a silicon carbide wafer for SIT processing, we buy it with the channel already deposited and the source already deposited. Now let's take a look at that a little bit more in detail. actually we can write up here. This distance here, the channel region in the gallium arsenide MOSFET was maybe 1,000 or 2,000 angstroms, 0.1, 0.2 microns. In a SIT, it is over 1 micron, and the source region here in turquoise is about on the order of a half a micron or so. So, again, let's see what this paragraph says is, because it's wide band, we can operate it without any problems at temperatures exceeding 500 degrees C. Great to put in car engines, jet engines, things like that. That operate at very high temperatures. In fact, it's the only material that is suitable for those very high temperatures. And let's see. Okay, let's take a look at the fabrication. So we start with, this is the wafer as purchased. It's about a 4-inch wafer. It's got a 1 micron channel width, and it has about a half micron source width. So that's out as purchased. So like the gallium arsenide wafer as purchased, and unlike silicon, the cost for the wafer before we even start the processing is quite high. So the first process is that we define the source and the trench, and we define these basically, they're called trenches. So we define that photolithographically, and we etch the source and the channel. So this is the source, turquoise. This is the channel in yellow. And now we're going to put a source contact, a metal source contact, and we're going to put gate metal on the sides of the trenches. So that is shown in the next two figures. First we put the source contact metal, and then we put the gate metal. So here we have the gate metal and the source metal. Now the interesting thing about these metals is saying, well, they're both metals, and of course that's true. However, they have very different properties. At the source, we want an ohmic contact. We don't want a Shockley here. That would be a disaster. So we want an ohmic contact at the source, but here we do want a Shockley. So an ohmic contact would be a disaster. So these are different metals. Generally, this is gold, and it is deposited and alloyed in a very different manner than the gate metal. We want to make sure that we have an ohmic contact here, but here we want to make sure that we have a Shockley. So while this is gold, this is a different metal. Generally, we use nickel, although I believe tungsten and even molybdenum can be used, but certainly not. I don't think we can use aluminum here. Generally, we could use aluminum, and this would be not alloyed like we have for the ohmic contact. We want to make a contact here where the metal is actually part of the source. So we alloy these at a relatively high temperature, whereas here, because it's a Shockley, we try to keep the temperature in the range of less than 700 degrees. So the gate metal is deposited first before the source metal. So this actually is backwards. I probably should have put the gate metal and then the ohmic metal, because the sequence follows gate metal and then source contact. And the other thing that one can see, it's maybe a little subtle, but boy, is it a big deal. The incredible difficulty in fabrication. We have to align the ohmic source metal to the source, and there can be no overlap whatsoever. If there's at least little spill off of this metal onto this region here, which is called the shoulder, the whole thing will become shorted. This distance here is about 0.3 to 0.4 microns. The ohmic contact will be somewhat less than that, say a quarter micron. So I have to align a quarter micron photolithography to a 0.4 micron or say, and with no misalignment allowed whatsoever. That is incredibly difficult to do. And then I got the other thing is I've got to somehow stick this gate metal onto the side of a 1 micron trench. The distance from here to here is about 1 micron. How in heaven's name do I put metal onto the side of this 1 micron structure without it spilling over onto this shoulder region? So these are two incredibly difficult alignments, and we can expect that the yield is going to be, to say the least, quite low. So, assuming we can do that, which is a huge assumption, let's take a look at a real device. Here we have the trench. This is a scanning electron microscope picture. We have the trench. This area here is called the shoulder. This is all silicon carbide. This region here is the source, and this is the source metal. So this is the source metal. The source is here, and this is the tiny little shoulder. And here we again have the gate. This is to not show the gate metal. The gate metal would be deposited on the sides of the trench. And the bottom line is only a very tiny number of these devices can be defective if the device is going to function. Generally, we'll have about 10, 15 to 20 of these things connected in parallel to make one transistor. So let's wrap things up, and what I've done here is some suggestions for general videos. These are non-technical. I've got lots of them, but I think these are the best of the best. They run anywhere from 30 to 45 minutes. 2 on the history of the transistor, 1 on the fabrication. The fabrication video, a little bit more involved than we got into in our discussion of fabrication, and 1 on the history of electricity. And I'd like to return to this kind of iconic picture that we've shown, I think, way back when in one of our very early sessions. These are the 3 inventors of the first transistor, the first solid state transistor. Start with Walter Brayton. He was the experimentalist. He was an engineer. He liked to make things. I don't think he would describe himself as a genius, but as a superb engineer. The 2 people here were a little bit more interesting, who can be described as geniuses, are John Bardeen and Bill Shockley. They're both geniuses, but both very different kinds of geniuses, and they both left very different legacies. So I'd like to start with the more interesting, more colorful, I guess, genius, Bill Shockley. He was more than a genius. He was a racist, a bigot, a eugenicist, and a downright nasty guy. Bardeen, also a genius, but the complete polar opposite. He was humble. He was an ideal husband, an ideal father, an ideal colleague, and he got along with everybody except one person, and that was Bill Shockley, whom he detested. Just one anecdote. I don't know if I mentioned this the last time. He enjoyed sports. He enjoyed playing sports. He enjoyed looking at sports, and he would go golfing every weekend. And on the week that he got the call from Sweden that he received the Nobel Prize, he played golf, and he didn't even mention the fact that he received the Nobel Prize to his golfing buddies. It just wasn't that important. So they both left legacies, and their legacies, I think, can be described in the titles of their biographies. The title of John Bardeen's biography is True Genius. The title of Bill Shockley's biography is Broken Genius. Their legacies are not described by their accomplishments. They were both geniuses, but rather that the adjectives that describe those accomplishments, one true and one broken. Okay, to end things up, I'd like to share with you the finale from the musical Showboat. The musical Showboat starts in the 1880s with Captain Andy and his daughter Nola, Gay Ravenel, and Queenie, and Julie, and all the people that we love. It goes on and ends in 1927. It's a long journey. In the interim, Gay, who is a gambler, goes bankrupt, and in shame, he but he decides to leave his wife Nola and his daughter Kim, and he comes back trying to maybe just glimpse his former love, and he starts singing the song, You Are Love, You Are Love. Wonder of all the world, where you go with me, heaven will always be.
Don't you know that? You taught me to sing one truth forever true. You are love.
Oh. There's a brand new water barrel up front. It's a mite like the old one.
Look, Gay.